Good morning, ma'am. Myself Ashita bearing a roll number 244Z580203 from Tribly branch. So, in control system, my topic is about concept of addition of zeros and poles. So, coming to the topic, first of all, what is mean by zero? So, the zero is nothing but negative of inverse of system time constant at which the magnitude of transfer function is zero. So, for example, here transfer function is s plus 4 into s minus 5 divided by s into s plus 1 into s minus 2 into s plus 3. In this, we can represent the zeros as 0 in the numerator part. So, here s plus 4 is equal to 0, s is equal to minus 4. So, minus 4 we can indicate 0. Next, s minus 5 is equals to 0, s is equals to plus 5. So, here we indicate 0. In denominator part, we can indicate the across marks, that is poles. So, s is equals to 0, the next pole. S plus 1 is equal to 0, s is equals to minus 1 is 1. Next, s is minus 2 is equals to 0, s is equals to plus 2. So here we indicate cross mark. X plus 3 is equals to 0, x is equals to minus 3. Next, the poles may affect the system response and system stability, but not the zeros. But for here, poles plays a major role. Thus, the system response will be differentiated, and the system stability also varies. Next, coming to the pole. What is mean by pole? The pole is nothing but negative of inverse of system time constant at which the magnitude of transfer function is infinity. So, for example, here there are no zeros, only poles are there. 1, 2, 3, 4 poles are there. S is equals to 0, 1 pole. S is equals to minus 1, 1 pole. S plus 2 is equals to 0, S is equals to minus 2, another pole. S plus 3 is equals to 0, S is equals to minus 3. They are the poles. In denominator part, we can represent the poles as cross mark, and in numerator part, we can indicate the zeros as 0 in the graph part. Figure closed clearly. Next, effect of zeros and poles to the g of s into h of s. Adding a pole to g of s has the effect of pushing the root locus towards the right half of s plane. So the complex path of the root locus bends towards the right. The angle of asymptotes reduces and the centroid is shifted to the left, and the system stability will be reduced. Next, adding of pole to g of s and h of s, the effect of moving the dominant portion of the root locus towards the right half of s plane, so that relative stability of the system is decreased by the addition of pole. So this is r of s is the input, y of s is the output. Again, we can feed back to the input through the feedback, that is h into h of s. Next, this is the gain part, g into s of s. So here is the error detector. So we can mix up the feedback input and the reference input also. Next, adding of zeros to the g of s and h of s. Adding a 0 to g of s h of s has the effect of pushing the root locus towards the left half of s plane, centroid shifted towards the right side, and the angle of asymptotes increases the path of the root locus bending towards left half of s plane, so that relative stability of the system is improved by the addition of 0. So the picture shows clearly. Next, relative stability. First of all, what is mean by relative stability? Relative stability indicates the closeness of the system to stable region. It is an indication of the strength or degree of the stability. In time domain, the relative stability may be measured by relative settling time of each root or pair of roots. If the root locus is located far away from the imaginary axis, then the transient dies out faster, so the relative stability of the system will be improved. Next, transfer function. So there is a clear representation. Poles are indicated by the cross and zeros are represented by the 0. So this is the minus 2 is the 0, and remaining minus 4, minus 3 are the poles in the S plane. Next, in x-axis we can take the infinity, and y-axis we can do the j is equals to s omega. This is the S plane of the transfer function. In transfer function we can locate all this one. Next, we can see one example, that is addition of poles. This is the transfer function. We can first step one is we can locate the zeros and poles. So here there are no zeros, and in poles there are 4 poles are there. One is 0, minus 1, minus 3, minus 5. So we can locate these poles in the S plane. Next, step 3, we can find out the asymptotes and centroid. This is the formula, plus or minus 180 into 2q plus 1 by divided by n minus m. And centroid formula, this is 0, minus 1, minus 3, minus 5, and minus 0 also. So this is the, we can minus 2.25, we can get the centroid. Next, step 4 then is we can find out the breakaway point. So in denominator part we can call as a characteristic equation. In this characteristic equation, we differentiate this equation and equate to that 0. We can find out the solutions. We can find out the roots of the transfer function. Next step is there are no complex roots. You know, step 6, we can find out the crossing point. So in the characteristic equation, we can place the s is equals to j omega, we can separate the imaginary part and real part. Thus we can find out the omega value and k value. So that s is equal to j omega means in place of omega we can place the omega value 1 point plus or minus 1.290. So this is the j omega. This is the problem regarding to the addition of poles and addition of zeros also. Same procedure we can follow. First one we can find out the zeros and pole. Here there are zeros are there. Minus 1 is the 0 and 0 minus 3 minus 5 are the poles. Step 2 is we can look at the poles and the zeros in the S plane. Third one we can find out the asymptotes and centroid. Fourth one is we can find out the characteristic equation. In that we can differentiate the from equal to the 0. Thus we can find out the roots. There are no complex roots are there. So step 5 is the crossing point. So same, separate the real part and imaginary part. We can get the omega value. Substitute this omega value in this s is equal to j omega. Thus we can find out the characteristic equation transfer function. So thank you ma'am for giving this opportunity. This is the whole presentation about my topic. Thank you.